Hello, welcome back to our discussions of Java. This time we're going to take a look at the object-oriented programming features of the Java language. So 4 characteristics of object-oriented programming languages: encapsulation, inheritance, polymorphism, and abstraction. We've seen 3 of these characteristics: encapsulation, inheritance, and polymorphism. Today we're going to get into the details of Java support for abstraction. Let's review the characteristics that we've seen before. Encapsulation. The class is the unit of encapsulation in Java, and it means that the class designer has the choice of what's visible outside. Typically, you have private data, private implementation data, and public methods. But you could also have private methods. The main thing here is that it's the designer's choice. Since it's the designer's choice what's visible outside, that's support for encapsulation. Inheritance. Inheritance is a process of reasoning from general to specific, and it helps in design. In inheritance, a derived class inherits the properties and methods of its base class. It extends those characteristics then, and becoming a more specific type. All Java classes inherit from object. So there's always inheritance. Whether you explicitly agree to it or not, you always inherit from object. Gaining, toString, and equals. Now we've seen how these methods behave if we don't override them. What does object's toString do? It does what it can. It presents the class name plus the memory location of the specific object. What else could it do? It doesn't, at the level that it is, it has no intuition about the business purpose of the class that you just designed. So it does what it can to implement a reasonable toString method. If you need a toString method for your business purposes, then you override that toString method with your specific details. Same thing for equals. What can object do with the equals method? It doesn't know, again, anything about the business purpose of the specific class. So it says, a reference comparison. Are these 2 objects at the same location in memory? If they are, they're equal. Otherwise, they're not. That's a shallow comparison, but that's what object can do. To get specific equals behavior, that is to look inside the object and say whether or not 2 objects are equal to one another, you need to override the equals method and implement a custom handling of that behavior that reflects your business logic. So we get reasonable behavior in object, but not specific, and that's general class design, right? As you get more and more specific, you can get more and more specific behavior. So let's look at inheritance in the physical world with an engine. So an engine is a machine that turns energy into movement. So a gasoline engine is an internal combustion engine, which is an engine. So this inheritance can help you think about the design of this. Once you understand engine and what it does, and then what an internal combustion engine does and how that's different, let's say, from an external combustion engine, and then understand what a gasoline engine does, that it inherits the characteristics of an internal combustion engine, but it uses gasoline, let's say, instead of diesel, right, in its specific implementation. Because object-oriented programming languages are meant to help us model objects in the real world, support for inheritance is really central to it, because that's how we engineer and think about objects in the real world. Polymorphism. Polymorphism means many forms, and it really depends on inheritance to work. It's really a related characteristic. So it means that an object handle can be declared as a more general type, but it will behave as the type that is actually instantiated. Instantiated here means the object instance is created with a new keyword. So for example, object O is set to a new student. We can do this because the student is an object. It won't work the other way around because not all objects are students. But because student will always inherit from object, eventually it's the top of the object hierarchy, we can declare this way. But when we do O.toString, if we've overridden the behavior of toString in the student object, we'll get the student's toString method. That's polymorphism. Abstraction. So abstract thinking is common, and And it's common to even the examples that we've previously done. Think about the engine, internal combustion engine, and then finally gasoline engine. I would say that internal combustion engine is also an abstract idea, right? The combustion is taking place inside, the fuel is being burnt inside the engine. Versus, let's say, an external combustion engine, such as a steam train, where the combustion is taking place outside the engine, right? Those are saying that it's an internal combustion engine is an abstract notion. Saying it's a gasoline engine is getting more specific, more concrete. Right? Let's think about animal. That's also an abstract notion. An animal eats, it moves, it breathes oxygen. But how does it eat? How does it move? How does it breathe? There's no critical, it's just an animal. In order to answer these questions, you'd have to know, let's say, the actual implementation. It's a fish, and so it eats, moves, and breathes oxygen in its own way. It's a cat. It eats, moves, and breathes oxygen in its own way. Those notions are still abstract notion. Cat, lion, leopard, house cat. We can recognize the commonalities in these animals, and behavior commonalities, and also physical commonalities. However, we know that they behave differently. Fish, also an abstract notion. It eats and moves and breathes oxygen differently. But then you'd have to get in, let's say, shark, white shark, versus flounder. So, reasoning in abstraction is very common. It's very common in the design of physical objects, in the engineering of physical objects, and it becomes valuable in our class design, in our object-oriented class design as well. We're pushing up the notion of reasoning from specific to general, and we're getting so general that we no longer know how the implementation will work. So object-oriented programming models real-world objects. The way we think about physical objects requires abstraction. It is natural, therefore, that the virtual objects of an object-oriented programming language support abstraction. Java supports abstraction in two ways, via the abstract base class and via the interface. Let's take a look. So the abstract class in Java, we make use of the keyword abstract. Look at the example. Add the keyword abstract to the class shape, and now you have an abstract class. That's really all you need to do. So you put it in the class, but it can also belong on the method. Notice here, we have an int color. That's actually partial implementation, because we say we're going to have a shape. Now look at draw. We know our shape has a color, and we may know at this point how that color will be implemented. So we implement it in the abstract class. Partial implementation. However, we also know that shapes can be drawn, but we don't know how it's going to be drawn until we know the exact shape. It's a square, it's a circle, it's an oval, right? It's a polyhedron, it's a pentagon. But whatever the shape is, that draw implementation will have to be specific to the shape. So we know that shapes can be drawn, but we don't know how at this level. We're asserting that we know what their color property looks like, and we know, for example, here with the method log color, we know a little bit how to deal with it. We're going to write to a log file the current color of the object. We know a little bit of how to deal with it. So an abstract class is in between. There's some implementation and some abstraction. Abstract classes cannot be used to create objects. So if you think about what an object needs, object equals new. If what's on the right-hand side of the new is an abstract class, the compiler won't let you do it, because the object won't have you said it's been declared that this is partial. It's a partial implementation. Therefore, you can't have an object out of it. That's like the real-world example, animal. We don't have ever an instance of something that's just an animal. So we will never have an instance of something in this situation that's just a shape. It's an abstract notion. So the objects require complete implementation of the methods. For example, here we do. Class square extends shape. So extends keyword, we've seen it with inheritance before, when you're inheriting from what's called a concrete class. A concrete class is a non-abstract class. And the compiler then will make you implement draw. It forces you to do it. because you promised you'd do it when you extended an abstract class. If you don't implement draw, square will also remain an abstract idea. So let's suppose you can't implement draw with square for whatever reason. You need to drive it further in order to know how it's going to be drawn. So square, let's say, remains to you in your class design to be an abstract class. What would you do there? You don't have a draw example. You'd put the keyword abstract in front of the class square, and now square is also abstract, and then you don't have to say anything about draw. But eventually you do. Eventually, in order to get an object out of it, some class has to implement draw. Let's look at interface. Interface is very similar in notion to an abstract class. However, it pushes it to the more extreme level. There's no implementation in an interface. So all it is method interfaces. Look at what we have here. Interface shape. So it's no longer abstract class. It's just the keyword interface. But it looks a lot like a class. So it has the name of the class, a name of the interface. It has the curly braces. And then within that curly braces, though, are just method headers. Notice what it looks like. It's the method without the body. So it ends in a semicolon. So instead of extending the class, you implement the shape. So when you implement an interface, you use the keyword implements. Look at class square, implement shape. It does the same thing as the abstract example. The compiler will make you then implement the draw method unless you declare your class as abstract. Okay? So you have to implement the draw method unless it's abstract. So let's take a look at the two examples side by side. A class extends a shape when the shape is an abstract-based class and therefore has to write the draw method. In the second example, when shape is an interface, class square implements shape, the rest of it's identical. You have to implement draw. So a class can be either concrete or abstract. Concrete meaning all methods are implemented. Abstract meaning it's explicitly declared as an abstract class, and some of the implementation left up to future work. In Java, you can only extend from one base class. So once you extend from a base class, that's all you can express. This avoids a lot of complications of inheriting the same implementation multiple times. When you implement an interface, however, you can implement any number of interfaces because interfaces don't have data. They're simpler things. They just have method names. So you can have a comma-separated list for implementation list. Much more flexible. So we're going to look next at an interface example in Java, and we're going to implement this. We have a drawable interface, a printable interface, and then we're going to implement a circle and a rectangle class that will implement those interfaces. So that'll be in the next lecture. See you then.